Somewhere in a lab right now, a machine is thinking, not like your laptop, not like your phone. It's thinking in a way no computer has ever thought before. And it's about to make everything you own feel ancient. For 80 years, computers followed one rule: do one thing at a time, very fast. That rule built the modern world, but that rule is running out of road. So engineers went looking for new rules. What they found is stranger, faster, and closer to nature than you'd expect. Let's start with the one you've already met: AI computing. Every time you talk to a chatbot or your phone finishes your sentence, you're using it. But AI computing isn't really about talking, it's about pattern matching at a massive scale. Think of a chef who has cooked 1,000,000 meals. Show him 3 ingredients, and he already knows the dish. He isn't guessing, he's remembering, instantly, from experience. AI chips work the same way. They don't calculate from scratch. They compare new information to patterns they've already learned. Millions of tiny calculations happen at once, not one after another. That's why AI feels so fast, and sometimes so eerily accurate. But there's a catch. This kind of thinking needs enormous power. Training a large AI model can burn through as much electricity as a small town uses in a day. So scientists asked a bold question: what if we stopped copying calculation and started copying the brain itself? That question led to neuromorphic computing. Your brain doesn't run on clock ticks and instructions. It runs on neurons, firing only when they have something to say. Picture a classroom where students only raise their hands when they actually know the answer. No noise, no wasted energy, just relevant signals at the right moment. Neuromorphic chips are built the same way. Instead of constantly processing data, they fire only when a signal changes. That means far less wasted power and much faster reactions to real-world events. A neuromorphic chip in a camera can spot motion in microseconds, using a tiny fraction of the energy a normal processor would need. It's efficient, it's elegant, but it still moves information the old-fashioned way, through electricity, down copper wires. And electricity, it turns out, has a speed limit that's becoming a problem, which is why some engineers stop using electricity altogether. Welcome to Photonic Computing, where information travels as light. Electricity moves fast, but light moves faster, and it barely heats up the wires it travels through. Imagine replacing every clogged highway with a beam of light that never hits traffic. That's the promise here. Photonic chips send data using tiny pulses of light instead of electrical current. Light beams can also cross each other without colliding, so photonic circuits can pack in far more information at once without overheating. Data centers already use light for long-distance cables. Now, engineers are shrinking that same idea onto a chip. The challenge is precision. Controlling light at that tiny scale is still difficult and expensive to manufacture reliably. Even so, light solves a problem that speed alone never could. The real question isn't how fast a computer can think, it's where that thinking actually happens. That question brings us to edge computing. Right now, a huge amount of computing happens far away, in giant data centers. Your request travels there, gets processed, and travels back. That round trip takes time. Imagine ordering food from a restaurant across the country instead of the one on your street. Edge computing puts the kitchen next door. Processing happens close to where the data is created. Inside your phone, your car, your doorbell camera. A self-driving car can't afford to wait for a distant server to decide whether to brake. It needs to decide in milliseconds, right where it stands. That's the power of the edge. Less waiting, faster reactions, less data traveling across the world. But not every device can carry a supercomputer inside it. Some tasks are simply too big for the edge to handle alone. For those tasks, we still need the giant brain in the sky: cloud computing. Think of cloud computing as a massive shared library, instead of everyone owning every book. Instead of your device doing all the heavy lifting, it borrows power from enormous data centers, packed with thousands of machines, working together. This is why your phone can edit a movie or run complex software without overheating in your pocket. The real work happens somewhere else, then the result gets sent straight back to you. It's efficient, flexible, and endlessly scalable. Need more power for one task? The cloud simply lends you more. But this system still has an old, stubborn bottleneck: Every one of these computers separates memory from processing, forcing data to constantly shuttle back and forth between the two. And that shuttle trip is quietly wasting enormous amounts of time. That bottleneck is exactly what in-memory computing was built to destroy. Normally, a computer stores information in one place and processes it in another. It's like a factory where the warehouse sits miles from the assembly line. Every single part has to be trucked back and forth before anything gets built. In-memory computing puts the warehouse and the factory in the same room. Processing happens directly inside the memory itself, so data doesn't need to travel nearly as far. That single change can make certain tasks dramatically faster, especially ones that involve huge amounts of data, like real-time analytics or scientific simulations. It's a simple idea with a powerful result. Cut the distance, and you cut the delay. But to truly merge memory and processing, engineers needed a completely new kind of component, something that could remember without needing constant power to do it. That component already exists. It's called a memristor. For decades, computers only had 3 basic building blocks. Now there's a 4th. A memristor is a tiny device that remembers how much electricity has passed through it, even after the power turns off. Imagine a water pipe that remembers exactly how much water flowed through it yesterday and adjusts itself based on that memory. That's essentially what a memristor does with electrical current. This lets a single component store information and process it at the same time, blurring the line between memory and computation entirely. Memristor-based chips could one day mimic how brain synapses strengthen with use, making machines that genuinely learn from experience at the hardware level. It's still an emerging technology, and mass production remains a serious challenge. But if it succeeds, it could rewrite the basic architecture computers have used for 80 years. Look at everything you just heard: machines that think in patterns, chips modeled on the brain, computers built from light instead of electricity, processing that lives on the edge, in the cloud, and inside memory itself, and a brand new building block that remembers on its own. Computing isn't just getting faster anymore. It's changing shape entirely. And this is only the beginning. Because outside the world of electricity and silicon, something even stranger is emerging. Machines that compute using quantum particles, machines that compute using strands of DNA. Molecules, biology, even magnetism are all being turned into tools for thought. In Part 2, we go beyond electricity itself and into computers that barely resemble computers at all. The next generation isn't coming, it's already being built, and it's going to look nothing like anything you've ever used before.